So today, learning objectives, of course, we're going to go back and look at, we're going to take a little smaller step here. We're going to look at the learning objectives for basically, like I said, a little bit of the history again here. So we're going to make a little chart first. That will help us remember this stuff. Identify historical examples of how basically with chemical substances meet their basic needs. That was back in the day here. Let's see how humans worked with chemical substances. Outline the role of evidence in the development of the atomic model consisting of protons, neutrons, and electrons for Dalton, Thompson, I should say, Rutherford, and Bohr. Okay. What we would consider to be matter? We're going to talk about this a little bit just because this term quite often comes up with some of these old people here, the history of the atom and things like that. So matter is anything that has a mass and takes up space. Solids are considered to be matter, of course. They take up space. Liquids take up space as well. And gases, okay? They do take up space, even though we can't sometimes always see them. They do take up space, okay? So matter is anything that has a mass and takes up space. Solids, liquids, or gases, okay? Developing ideas about matter. Ancestors of the First Nations people used their knowledge about the nature of matter and its processes to help them meet their basic needs. They did have knowledge about the use of plants, so fire, and of course states of matter. Okay, how do they use this knowledge? What do you think they did with these things to help them? Okay, knowledge about plants, fire, states of matter. What would they use those things for? Making medicine, sure, from plants usually, yes. In most cases. What about fire? Obviously to cook food, yeah, sure. And states of matter, right? Melting water, for example, if it was ice or whatever, into liquids, okay? So, developing ideas about matter. Cooking food was an important step in human survival, and so was the development of food preservation techniques such as the following. We probably should write this down, guys. So, developing ideas about matter. Cooking food, okay, was a really important, of course. Okay. So cooking food, obviously important, you know, important use of fire. Heating and freezing, different states, right? Understanding that. Salting, so salting, curing process basically. Smoking food, once again, the use of a flame to smoke their food, okay? And fermentation, so making of beer and wine, okay? So that's what they would use those things for. Developing ideas about matter. Metallurgy was an early branch of chemistry that dealt with producing and using metals. So the idea about matter back in the time was metallurgy. And once again, they would use these different metals probably to help themselves build, you know, back in the day, cooking utensils, whatever they needed, basically, any of the important things that they would need, right? So metallurgy was an early branch of chemistry that dealt with producing and using metals, metallurgy, okay? So that was part of the idea about matter as well, okay? Metallurgy also helped them make, for example, arrow tips, right, for hunting, things like that, so they could collect food, etc. All right, so we're going to go back to, like I said, earlier days here. Aristotle's description of matter. Probably a few things you want to write down is probably the year for right now. So the year was 400 BCE, or basically BC, before Common Era is what we call that. And Aristotle, you don't have to write all this stuff down, guys, but Aristotle, remember, his big thing was everything is made up of the four elements: earth, air, fire, and water. Okay? So he had these four elements. That's what he said everything is made up of. And like I said, we talked about this actually before in the notes, right? He had a lot of influence on people. He was very famous. He's like, hey, everything's made up of earth, air, fire, and water. And people are like, okay, he knows what he's talking about. Let's go with this guy. So he had a lot of influence, and so people believed him for over 2,000 years. Okay, that's how much people respected him, basically. So Aristotle, 400 BCE, and he said that matter is made up of 4 elements: earth, air, fire, and water. Okay, so, and you don't have to copy down the little graph thing there or anything like that. That's in your notes there. Okay, and you don't have to copy that on the fact that we know that he had, well, I guess you could if you want to, but we've talked about that before. He had a lot of influence over people. Okay. Democritus, remember, he was the one that said, no, there is such thing as the smallest part, the smallest indivisible particle kind of thing. So he was also in 400 BCE, but remember, he wasn't as famous. People didn't believe him. Okay, matter is made up of tiny particles that cannot be broken down further. These particles were called atomos, which was Greek for being indivisible. Okay, can't break it down. They're indivisible. Different elements were composed of different kinds of atoms, and this was not accepted at the time, of course. Okay. So once again, I would probably write down his name here, guys. Democritus, 400 BCE, and remember, he had tiny particles. He believed in the tiny particles, and originally they were called atomos, which means, like I said, Greek for indivisible. He said different elements were different kinds of these atoms, and that was pretty. That's pretty true. Like, that's carbon's different than nitrogen or oxygen. All these different atoms are different stuff. It was not accepted at the time because, of course, he wasn't as famous. Plus, we talked about this before. Why else did they not accept his theory, Sarah? Yeah, you'd see fire and water and air and things like that. You could see that stuff, right? But you can't see atoms, right? So they were like, well, whatever, this guy's full of it, right? Yeah. Okay, so then in 1650, okay, 1650, Robert Boyle came along, and he did not believe in the 4. This guy's new for us. Really, in the big scheme of things, we don't really probably need to know this guy as much. He's not as famous as the other ones, but nonetheless, in 1650, he did not believe in the 4-element model, and he discovered that even gases are made up of tiny particles that group together to make substances. So he did not believe in this air and earth and fire and water kind of thing. Okay, he did not believe in that. So that was Boyle in 1650. Okay. And around this time, there became many models of atoms that were proposed. So around this time is when we started getting into, we talked about these guys before, Thompson, Rutherford, I think guys like that, who came up with lots of different models of atoms at this time. Okay, so this is where we start to actually figure out some of the history of the atom, basically based on that. Okay. So Boyle, 1650, he did not believe in the 4-element model. Okay, and this is at about the same time when other people started coming up with theories about the atom. Okay, so here's what we're going to do. We're going to make this little table in our books here. Okay, don't have to write this part down here, guys, at the top. So just know we're going to do Dalton, Thompson, Rutherford, Bohr. Okay. And if you want, I'll write those out a little bit bigger for you. So let's make this table, and I'll talk about, I know it's kind of small, but we'll go through these. And this is what you're going to fill in from the notes here coming up. All right? So, once again, Dalton, Thompson, this is Rutherford here, and Bohr. Okay. And we're going to fill these in here for the year, the experiment he did. Okay, so year, experiment, the atomic model, if we can kind of come up with one, and a diagram for that. model if we can. Okay, so year, experiment, atomic model, and the diagram for that atomic model. Okay, I don't know if we'll be able to fill in all exact squares, but that's fine. Okay, we'll make this table here. So once again, Dalton, Thompson, Rutherford, Bohr, and we're going to make the year, experiment, atomic model, and a diagram that goes with that. Okay. All right. So John Dalton, 1808. Okay. And his experiment, he based his model of the atom on experiments he did where he combined elements to form new compounds. So I guess if you want to write something down about that, what's his experiment? I would say probably combined atoms to form new compounds. Okay. If you want to just shorten that somehow, maybe elements to compounds or combined elements, compounds. Okay. If you want a diagram of that, I'd say probably an example would be this here. Carbon and oxygens give you carbon dioxide, something like that there, and you can just write it even just simple as that. Okay. That would be an experiment there for him. Or sorry, a diagram, I guess you could say. Diagram. So 1808, atomic model of matter. So what's his atomic model basically is all matter is made up of atoms which are small to see. Each element has its own kind of atom with its own particular mass. Actually, I think this is in your notes already, so you don't have to worry about this part, okay? So this is already on Google Classroom, guys. Each element has its own kind of atom with its own particular mass. Compounds are created when atoms of different elements link to form molecules. Example, water. Atoms cannot be created, destroyed, or subdivided in chemical changes. So that's what he believed about his model, atomic model theory. Okay, like I said, that's in Google Classroom. It's actually in this chart that you'll see there. Okay, so it's already there for you filled out. Okay, so don't worry about that too much. Okay, all right. J.J. Thompson was in the 1890s, okay, and he discovered the electron. Okay, discovered the electron. His experiments showed that atoms contain small negatively charged particles, and he developed the raisin bun or plum pudding model. Okay, I guess you could probably, I mean, if you wanted to, you could probably. When I look at that, I think I see chocolate chip cookie is what I see. Probably because I like chocolate chip cookies, but that's what it looks like to me. I don't know about you, but you know, atoms contain small negatively charged particles called electrons, which are the raisins or the chocolate chips there, you could say. Okay, the rest of the atom is a sphere of positive charge, and that's the bun or the actual cookie part. Okay, and the overall atom has a net neutral charge or a neutral charge. So basically, he was saying that the sphere here part, this cookie or this bun here was the positive, the raisins were embedded in it, and those were the negatives. Okay. So he had basically, if you want to consider a model or a diagram there, that's what you'd be filling in there. Okay, so the diagram at the end, or the model basically was that it's a sphere of positive charges with electrons that were embedded inside of it, negative particles. Okay, the electrons. So that was Thompson's idea on what his model looked like. Okay. His experiments showed that atoms contain small negatively charged particles. Those negatively charged particles were the raisins or the chocolate chips that you see there, kind of thing. And the positive sphere was that bun or the chocolate chip cookie, the cookie part. Okay. All right. His design, his experiment was based on this. Okay, and this will be Actually, I don't think I put this in the notes because it's not the end of the world if you don't have this, but I don't think I put this in the notes here. But J.J. Thompson's cathode ray tube, okay? So basically he would pump stuff into this, okay? And there was a positively charged metal plate at this end and a negatively charged plate at this end, and you would see that different compounds, different atoms or whatever would go up or down based on what they were, okay? So based on that, that's kind of what his model or his experiment was. It was, if you want to put experiment there, just put cathode ray tube. It's probably fine. Cathode ray tube. CRT. They used to use those in TVs back in the day, okay, and that's how they displayed the picture way back when. Now you got, well, I'm still from the old school. I got plasma, okay? Don't use plasma anymore. Now you guys, what is it? LEDs, 4K LED, blah blah blah, right? Well, back in the day we had CRTs, cathode ray tubes, okay? All right. Rutherford is 1909. His experiment was, if you remember this, we talked about this one earlier too. This is where he takes the positively charged alpha particle and fires it at a sheet of gold foil. Okay. So he took a alpha particle, if you want to summarize that, alpha particle, shot it at gold foil. Okay. Alpha particle at gold foil. So that's his experiment, and I think I have a picture here coming up here for you. But instead of the alpha particle passing straight through, all these gold, basically the gold atoms, really is what they are, a bunch of gold atoms linked together. Instead of them passing right through, what happened was some were bouncing back, okay, or getting deflected in some cases. So, and he had that little, he had like a curtain set up behind kind of thing that measured that. So some bounced back, and he knew that the positively charged particles repel one another, but he also knew that if we had this positive sphere, it wasn't enough to deflect. It wasn't strong enough to, if I shot something at it, it wasn't strong enough to bounce it back. So then he realized that, hey, yeah, there might be a positive part there, but it's not due to repulsion. It's not bouncing back because that's positive and this alpha particle is positive, etc. So this cloud would not have been strong enough to repel that, okay? Here's the gold atoms here. And like he said, he had kind of a curtain here set up, okay? So these are the positive particles here, and you had this. And he would notice that somewhere, this is kind of what he was thinking would happen. You'd shoot them, they might go right through kind of thing, or they would get deflected a little bit, you know, a little bit. But what was happening was some were actually hitting and coming back, okay, or getting deflected pretty severely and coming back. Some were still passing through because they didn't hit, what's this called, by the way, of the atom? What would that be called? The nucleus. So some were not hitting the nucleus, so they would be passing right through, but others were hitting the nucleus, and that's why they were bouncing back or getting deflected, okay? So then that's what he said. Well, I said, well, there's got to be something going on there, and so that was his kind of diagram of what was happening, okay? Shooting these particles at this gold foil, basically, and having some of these particles bounce back at him, okay? All right. So, like I said, this is kind of what he expected to happen, and this is really what did happen. Some passed through, but some bounced back. Some were deflected quite severely, which basically means that there has to be a dense something in the middle of this atom, okay? So his Ernest Rutherford's model here, that was what? That was, yeah, Rutherford. So his model, okay, the nuclear model, An atom has a tiny, dense, positive core called the nucleus that contains protons, and that's what he came up with. So he said those positive particles actually have a home in the middle of the nucleus, or in the middle of that atom, and it's called the nucleus. Okay? And the nucleus is mostly empty space that contains rapidly moving electrons, and that's why most of the alpha particles pass straight through, yet a few did not, and they bounced back. Okay? So here's the protons here. This is what he thought, Rutherford. Protons right here, you can draw this if you want, and the electrons go around the outside. Okay? So they orbit around the outside, and when he shot the particle, some would go right through, and some would hit the nucleus and bounce back. Okay? So his idea of the model looks like that. Rutherford's atom basically looks like that. And once again, you can draw that for the diagram there, guys. Positive nucleus, okay? And then electrons going around the outside, basically. That was his thinking there, okay? So positive nucleus. And you don't have to draw all the rings like that per se. If you want, you can, whatever. But basically, just draw some electrons around the outside. And that's what his theory was. Okay, that's what his model looks like. Okay? Is that good? Yes? Okay. And finally, okay, Niels Bohr. So 1885 to 1962. 1962 wasn't that long ago, right? His experiment when you heat elements in a flame, they show a few specific colors that can be observed with a spectroscope. Okay, these colors are called a line spectrum. Okay, so Niels Bohr, 1885 to 1962, and basically all I need to write down about the experiment is basically that he heated up elements in a flame. Okay, and they show specific colors when that happens. All right. The Bohr model explains the light spectrum observed. When electrons are energized by heat, electricity, or light, they can jump from a lower energy level to a higher energy level. And the electrons return to their ground state when it gives off light. So I think we talked about that before in the notes. What's some examples of that? Yep. Neon. Yep. What's another one? You're really going to make me do this? Yeah. Are you sure? Ooh, ooh. Ooh, ooh. Glow sticks. I was at a dance party there in case you didn't figure that. You didn't. Glow sticks. Yeah. Neon, right? Fluorescent clothing, things like that. So when light hits those things, it takes in the energy, excites the electrons to the next energy level, and when the light goes away, they jump back down. And when they jump back down to the lower energy level, they give off that energy in the form of light. Okay, so glow sticks. What was the other one? Whoa, who said the other one there? Neon. Okay, when you plug in a sign, things like that. Okay, so electrons turn back to their ground state. A different color of light will be given off depending on what energy level the electron starts from and jumps to. So perhaps don't copy this one down because I got a better diagram than this. But as they go up and when they start coming back down, they will give off different energies of lights. Okay. So here's Niels Bohr model. Okay, and that's probably a better diagram here. Yeah. Okay. So Niels Bohr in 1885 posed that electrons surround the positively charged nucleus at specific energy levels, and the different energy levels explain the different colors that were observed. Okay, so that'd be an example of his model. Nucleus containing positively charged protons, and then here's the electrons around the outside. Okay. All right. What are we still missing from the atom so far? What's missing? What's missing? What do you think? Neutrons, yeah. Where do neutrons go, by the way? In with the protons, right? So what we're missing here is still the neutrons, yes? So we'll get to that eventually. But protons go in here. Neutrons also go in here. And when we're talking about the weight of an atom, it all comes from here, okay? Electrons, comparatively speaking, weigh nothing. Protons and neutrons are where all the mass comes from, okay? So we are still missing neutrons, of course, okay? So that was Bohr, 1885. That should fill in most of it for you there, I think. His atomic model looks like that there for you, okay? All right. Oh, there we go. Evidence of the neutron, okay? So Rutherford and Chadwick proposed that there was a third subatomic particle called a neutron, okay? Now I need you to pay attention to this because I think there is a question in your homework here today. He noticed that helium contained twice as many protons and electrons as hydrogen. So hydrogen has one proton, okay? Hydrogen has one proton and one electron because we want it to be neutral, okay? Helium has two protons and two electrons, okay? And once again, we want the protons and electrons, we want them to be the same in this part so far because it's a neutral atom, okay? However, helium is 4 times heavier than hydrogen. So how? That is 4 times heavier than that. But yet there's only two, like there's only an extra proton and an extra electron. So how is that possible? And the answer is, of course, it is due to the number of neutrons, okay? So hydrogen, how many neutrons does hydrogen have? Do you guys remember? You guys know? Well, it's got a number of atomic number of 1, and it weighs 1, basically 1.01, but 1. So how many neutrons is there? The answer is 0. Okay. Helium has 2 protons, yet it weighs 4. Okay. So what is missing there? Some neutrons. Yes. Okay. And finally, so those guys were responsible for the neutron, of course. And finally, we have what we call the quantum mechanic model. Okay, and this is where I kind of start in Chem 20. When I teach Chem 20, we start with what's called the quantum mechanic model. And the quantum mechanic model says basically electrons are considered to be a cloud around the nucleus. Okay. There's a bunch of them. Some are close to the nucleus, some are farther away from the nucleus. In the nucleus, of course, in this nucleus right here, it's not a great diagram. You have your protons and neutrons in the nucleus, okay? And your electrons just kind of surround that nucleus. Bohr said there's specific energy levels for those. And after a little bit more research, we found that yes, there is kind of, but really there's no set level, energy level that they're on. So they might be very close to the nucleus, okay? And that's kind of where you find most of the electrons, of course. They always fill up closest to the nucleus first. And then as you get farther and farther away from the nucleus, they're less and less likely to be found. So basically as you get farther and farther out, they kind of start to spread out a little bit farther there, okay? But you would find the majority of the electrons closest to the nucleus. That's how they get filled up first. Okay, closest to the nucleus, and then they start to expand outwards. Okay, so that's kind of the history of that. Okay, and this is kind of what we believe today. We still use Bohr diagrams today. We'll do that. In fact, we're going to do that next class. We're still going to use Bohr diagrams. Still use them in Chem 20. They're still valuable. Okay, they're nice and neat. They're not an electron cloud. We can specifically put electrons where we want them, and that's important for us as well. But this is probably a little bit more accurate. Okay. All right. So that should be the end of that. You guys have a worksheet that you guys need to fill in there, so you guys can go to Google Classroom and fill that in here. We've got a little bit of time left, so you probably should be able to get that done today here. And once again, there's a copy of the notes in Google Classroom as well, so there's a copy of all that stuff there too to help you answer any of the questions. Okay? Let's see here. Yeah.